basing on the formula to calculate the work. All right. And then you have, in the realities, you have many forms of energy. For example, you have the kinetic energy, from previous chapter. You have potential energy. So potential energy, like we already know, gravitational potential energy. Or you can know the light energy. So the energy coming from the light, and the thermal energy, right? When you feel cold and then you need some heat, so that is a thermal energy. And also very popular, everybody need it, it's electrical energy. Okay. And very, very strong, a lot of energy is nuclear energy, which the nuclear energy, which to transfer to the electrical energy. And also, you have different forms energy, and these forms energy, they can transfer from this form of energy to another form of energy. Okay. For example, some kinetic energy can transform to potential energy, or to light energy, or thermal energy, or electrical energy, right? You know this in the reality. And also from this one, you can transfer to nuclear electrical energy. That is the way people now trying to have the electrical energy from the nuclear energy, because it's a very rich source of the energy. So what is in this course, you learn about the mechanics. So the mechanics, you will have called the mechanical energy. Mechanical energy for the mechanics. So the mechanical energy containing kinetic energy and potential energy. Okay. So the kinetic energy I denote as K, and potential energy I denote as U. All right. So some of this one is called mechanical energy, and in this course, you will pay more attention on the mechanical energy and also the conservation of the mechanical energy. That is great. So the kinetic energy is the energy that body pulls due to its motion. Due to its motion. So K is equal to 1/2 mv squared. So due to its motion means, if V0 means no motion, you don't have the kinetic energy. Okay. And V not 0, and then you have the motion. You have the motion. And then K is not 0. That is what I mean, right? You don't have motion, you don't have the kinetic energy. And vice versa. If you have the kinetic energy, means that the velocity is not 0. If I provide you some kinetic energy, you have to move. And vice versa. If you are moving, then you will have inside you the kinetic energy. That is me. So you remember the kinetic energy always connect to the velocity of the objects. They have this relation. Okay. They don't care any other parameters, that only related to the velocity in the motion. Of course, the object should have mass. Okay. If if no mass and then no energy, no mass and no energy. If you have mass, then also you need to have the velocity, then you have the kinetic energy. What is potential energy? So the potential energy is energy stored in an object due to its position and its state of shape. So actually, its position, later I will explain more. But for the position, it will be related to the gravitational potential. And state of the shape, we are related to the elastic potential. Elastic. You already know the Hooke's law, right? When the spring is change the shape, and it appears some force, and this force creates some potential, and it is related to the elastic potential, right? So some type of potential energy is you know, the chemical energy. Chemical energy is some you change from the, I think you have this course, right? From this ion to this another ion to exchange ions, so it creates some mechanical energy from this type atom to another, right? Obeying the chemical process. Also, this related, as I have just mentioned, the gravitational potential and elastic potential. That is, so you pay attention to this type of the energy. All right. And of course, between this type of energy, it can transform to another type of the energy. We move to the this. So the energy conservations. So as I mentioned, the energy can be converted or transformed to another forms of energy. So we can say that it's convert from one form to another, right? But when you have the energy conservation, we know later, some of them will be conserved. And for the converting the energy from one form to another, we have the parameters is called the efficiency. What is the efficiency? So the efficiency of some device used to convert one form of energy into another will be defined as the fraction of useful energy output divided by total energy input. For example, if you you have a fan, right? Fan. So you need the fan will convert from the electrical energy to some mechanical energy, right? Energy. So you not all this total electrical energy transform to or convert to mechanical energy. There are some energy loss for the heat, for example, and so on. So this energy is you want to receive is called useful. This is a total. So the efficiency is defined as the fraction of useful in energy output. This output, right? Divided by total energy input. So this give you, sometimes you multiply by 100% to know that how many percent of the total energy transfer to the energy you want to get or to be converted. Okay. That is a definition, some definitions. We move to the next slide. So in this slide, let me do it this small. We make some example. One example for the energy conservation, and also if we know there's some process to convert from this type of energy to another type or another form of energy. That is, we consider the free fall motion. Okay, in the free fall motion, so we learn from the chapter 1 for the free fall motion. So now I will consider that. So for example, we have the ground here. Okay, so one object is falling from rest, for example, and then is falling down. All right, until it gets the ground. So I denote this position is A, this position is B, or the position is the first position is number 1, and this number 2. Okay, so initial position is number 1, and the final position is number 2. And then at this position, the object has the velocity v1, and here is v2, and the height is h1, h2, okay. So that is the positions. And it is moving from 1 to number 2. So from the kinematics, you have this relation, right? You have the relation different in the v square. v2 square minus v1 square, v equal to 2a s. So you know what is A, right? A is equal to gravitational free fall motion, downwards, vertically downward. Okay, A equal to G. And how about S? S is the vector of the transition, pointing from this to this. So S is actually is this vector. Okay, S is this vector, and S this vector multiplied by G this vector. So two vectors, they are parallel to each other. So the magnitude is 2GS, where the S equal to h1 minus h2, right? I mean the magnitude, no vector here is magnitude, is h1 minus h2 because h1 greater than h2 in this case. So here maybe you think about the vector vector expressions. So vector h2 is this vector minus this h1 is vector. So maybe you take this vector, subtract to this vector, also you get this vector. It's the same, right? This expression is the same, but you can do by this way, another way. So this 2G h1 minus h2. All right. So then from here, you have V2 square minus V1 square equal to 2G81 minus 2G is 2. And then if I multiply both sides by the factor of m/2, okay, m/2, then I will have m v2 square divided by 2 minus m v1 square divided by 2 is equal to m g81 minus m g82. So I take the number 2 on one side, number 1 in another side. So I will have 1/2 m v2 square plus m g82 equal to m v1 square divided by 2 plus m g81. Okay, so you see, this is number 2, this is number 1. So it's somehow sum of these two quantities after position 2 and position 1 doesn't change or conserve. And then you call this one is mechanical energy. So the mechanical energy of the objects is defined by mv squared divided by 2 plus mg8, where this one is kinetic energy and this one mg8 is potential energy. So the potential is mg and the height of the object comparing to the place you take the origin to calculate the potential. Okay, and some of them is called the mechanical energy, and then you know E equal to K plus U. If you take the changing in the mechanical energy, you call delta E. Delta E is a changing, means delta E equal to E2 minus E1, right? And from here, this guy, E left hand side is E after position 2, is E after position 1. Delta E is equal to E2 minus E1 is equal to 0, right? Will be equal to delta K. Delta K will be here. Delta K, yeah. mv2 square minus mv1 square. Here is delta K. And the right hand side, mg1 minus mg2. So it's minus delta U. Okay, so delta K plus delta U. But from here you have delta K, but delta K equal to minus delta U. So delta E become to 0, or vice versa. If delta E equal to 0, then you have delta K equal to minus delta E. So this is two directions. You have two directions. Delta E equal to 0. Then you have delta K equal to minus delta U, or vice versa. So what does it mean? Delta K equal to minus delta U. How much you increase in the kinetic energy, and the same amount you decrease the potential energy, so that some of them doesn't change. Okay? Any question? Is it clear? So obviously, as we did before, nothing new, we get the energy conservation of the free fall motion. If we neglect the air resistance, okay, that is called free fall. And in this slide, we learn about the work, the relation between work and kinetic energy. All right. So what is the work? When you talk about the work, that is the work done by any force. So for example, I consider the motions for example, this the floor or the table, and I have an object on this surface. Okay. So if we analyze the force acting on this object is from the previous chapter, we have the gravitational force and the normal force. All right. So if we add some force to this object, the F, push it, make it moving from left to right. And it's moving to this new position. This is a new position at all. This is a new position. And then it's moved with the distance S. S vector means is pointing from the initial position to the final position. So vector S is this vector. Okay. So the work, I say that the work done by the force F, we define as the scalar product between F. This I take the small f, so you can take the small f to be consistent. F and S, scalar product. So the scalar product will be equal to the magnitude of F, right? And magnitude of S, and the cosines between these two vectors. The alpha is the angle created from the direction of the force and the direction of the motion. Okay. So formula is correct in the case of the force, doesn't vary with position. So F is constant. Doesn't change during the motion of the objects. So who can give me some example? One example so that the force changes when the position of the object changes.
Could it be free falling?
Yeah. Who is talking?
It's me.
Whom, right? Then whom? Yeah, to whom can you say again?
I was saying that it could be free falling because
Free
the
falling.
change and kinetic energy also change.
But in the free fall motion, we consider the force acting on the object is the gravitational force doesn't change. Right?
Okay.
Right? Yeah. We assume that the gravitational force is constant during this motion. So that the acceleration doesn't change. Yeah.
How about the acceleration of an object?
Yeah, right. In the free fall motion, the acceleration of the objects doesn't change. It's constant. That is why you have the motion with the constant acceleration. Z is constant.
Thank you, Professor.
In fact, this one is not perfect constant. It can be changed because later you will know, if you look at more deeply on this one, this will be depend on the height of the objects, the distance. So we have, I understand what you mean. The center of the earth is here, right? It's the surface. So this appear because they are attract between this mass to this. So it depends on the distance. If we learn the force law of Newton, we don't have time to learn at this course. But obviously, this depends on the distance from this object to the center of the earth. So when you are moving, the distance is changed. But the changing in this is very, very small comparing to g, because this distance very, very small comparing to the radius of the earth. Radius of the earth is here. Too small. So that if you consider the motion of the object very close to the surface of the earth, we consider the gravitational acceleration is constant, or the force, this force, gravitational force, be constant for the objects moving close to the surface of the earth. Okay, cool.
Yes, thank you, Professor.
Okay, so if someone else give me an example.
I think the force from a spring.
Very good. Thanks, Dietling. Very nice. The spring is a Hooke's law, right? So you see, F is K delta L, the magnitude. So it depending on the extension of the spring. So the expansion of the spring is decided by the position of the object. When the object is moving. So the position of the object will give you the different extension on the spring. And in this case, the force made by the spring acting on the object will change depending on the position, vary. All right. So remember that this formula only correct in case of F constant. Remember, if F is not constant, we need another formula. Okay, I will talk about it later. All right. So this is the work, okay? And now I will introduce the work kinetic energy theory. Work kinetic energy theory. What is it? Here. So let me give you this one. Let me talk about a little bit about the work for some special case so that you know this. F and S, this alpha. So the work done by the F in general, any force, will be equal to Fs equal to Fs force alpha. So from this formula, you know that because it depending on the angle. So this will be 0 if cos 0. Cos 0 is alpha equal to pi over 2. Agree? So in the case like this, f like this, it doesn't make any work. Okay? If you know, if you push the lattice, it takes it. The lattice cannot move because you didn't done the work. So when alpha is a positive or greater than 0, if alpha is greater than 0, smaller than pi over 2, okay, is you have cosine alpha positive. So if we did positive work or the negative work, it get negative value or smaller than 0 if alpha greater than pi over 2. So in the case like this, f is negative. And when f negative, the force is a restrict the motion, you will know from this theory. So the work kinetic energy give you delta K equal to work. So what does it mean? Delta K is a changing in the in kinetic energy. So this position 1 is move this to the position 2. Okay, it's moving from 1 to 2 with the distance s. So the changing in the kinetic energy, that is delta K will be equal to K2 minus K1. The work kinetic energy theorem saying that this will be equal to the work done by all the force acting on the object. So if when you calculate the force, all the force work acting on the object will be two case. You will do one by one. Work done by F, work done by all the force, right? P, gravitational force, normal force, all the force acting on the object. You will calculate one by one, and then you sum of them, or you take F total equal to F plus N plus P. You sum of all of them to get this value, and this will be equal to F total. Okay? But normally we calculate by this way. So if you calculate by this way, you know this force and this force, they cancel out each other. So the remaining only one, this F. Or another way is the work by the normal force is perpendicular to the distance. So this work will be 0. The also gravitational force 0 because the motion is perpendicular in this case. Okay. So remaining only the work done by the F along the direction of motion. So you have this theory. This means that. So now we can prove this formula, start using this relation. Okay. So you have V2 squared equal to V1 squared plus 2AS. Agree? So in fact, you have V2 squared minus V1 squared equal to 2AS. So from here, you multiply by the mass over 2 on both sides. M over 2, M over 2. So on the left hand side, you have K2 minus K1 equal to M A S. And you know what is MA? The second law of Newton telling that is the total force acting on the object. So then you have different in the kinetic energy, the changing in the kinetic energy equal to work done by the total force acting on the object. So we get this formula. Work F total will be equal to delta K. Remember, this is the most important theorems in case of the mechanical, we get the mechanical energy conservation. Is it clear? Remember, changing in the kinetic energy equal to the work done by all the force acting on the object. So now we make an example. Now we make a simple example to apply these theorems to find back the energy conservation during free fall motion. Okay. So I will make this example for you to us. These are grounds. The object is here. So the position, I will go back. This is a position 1. This is a position 2. Is the height H2, V2, H1, V1. Now we apply this theory to get back the energy conservation as before we did. So the force acting on the object is gravitational force. Okay, agree? Only gravitational force, that is a free fall motion. So according to this, you have changing in the kinetic energy, K2 minus K1 equal to the work done by the gravitational force, right? Because only gravitational force acting on the objects will be Ps. S is the distance from here to here. S, P, they are in the same direction. So in the magnitude, they have P, S. That is mg H1 minus H2 because S equal to H1 minus H2, right? So from here, you get V squared minus 1/2 mv1 squared equal to mg H1 minus mg H2, and then you get back easily the energy conservation as you get before. So 1/2 mv squared plus mg H2 equal to mv1 squared over 2 plus mg H1. Agree? So E2 equal to E1, energy conservation equal to E is constant. Okay? So in this example, you don't need to apply this formula anymore. You apply directly this theory. Changing in the kinetic energy equal to the work done by all the force acting on the object. And then you just calculate the work. It's okay? You will do several exercise using this theory. Any question?
I have a question.
Yeah?
I already charged for you.
Sorry. Particle move along x-axis is a velocity change from minus the work done on the particle is a positive or negative or zero. Okay. So I remind you the work done by a force. So in your case, you don't know the direction of the force, but you know the velocity of the objects from the position 1 to position 2. And you said that the velocity v1 equal to what? Can you read? -3, right?
Yeah.
-3 v2 -2, right? So this we decrease the speed. So then the k is 1/2 v2 square m minus 1/2 m v1 square. Will be negative or positive? Negative. Agree? Because v2 square greater than smaller than v1 square is negative. And then this equal to work done by the force is a negative. So in this case, if you move from 1 to 2, 1 to 2, so S is like this, and the force have to pointing with the angle greater than pi/2. So this resistance force. Minh Đức, is it okay?
Yeah.
Yeah. So the signs of the velocity, it doesn't matter. But it matter is the speed. It's the absolute value. How change the speed? Okay. You have the deceleration or acceleration. That is important. Sorry. So you have the acceleration. If the object need to be accelerated, if we have the work done, it's a positive. Deceleration, the work is be negative. It's okay. And then when you calculate the work done, is the work positive or negative? Is depending on not the velocity but the direction of motion. The transition, direction of transition. Where is the position 1 and where is the position, and then you pointing the vector S from the initial place to the final place. And the direction of the force. Okay, so if you have positive work done, you need to act the force. If you want to accelerate the object, you need to act the force, creating an angle with the transition as smaller than pi/2. If you want to decrease it, deceleration decreases, you need to act the force in the direction greater pi/2. Okay, that's the main point. It's a good question. Thank you, Huỳnh Đức. Any other question? Okay, right, it's clear. All right, so in this slide, I will introduce in the case of it's very small. Oh. So far, we know the formula of the work done by a constant force. The force doesn't vary with the position. How about in the case of the force, depending on the position of the object? So in this case, for example, if you take the origin here, the object, for example, the object is here. So the position of the object in general determined by this vector. Sorry. So this gives you the position of the objects. And then when the object moves to another place, R1, right? Position 1, position 2. So then the position give you 2. Okay? So now the force F R1. Force after position R1. And this one is the force after position R2. Okay? So in this case, you set up the F depending on the position, because F at the position R1 is not the same as force at the position R2. That is mean of this. So in this case, how we can calculate the work done by this force? So in this case, if we consider the motion of the object is a very small position. So from position 1 to 1 prime, the transaction is delta R very small. Delta R very small. Delta R is R2 minus R1. Delta R is actually this. Delta R actually is a vector S, right? So if delta R very small, changing in the position. So when it's small, then you can consider as in this changing, F is constant. So that you can calculate in this case, the work done by the force will be equal to the force multiplied by the delta R very small. Delta R is S, right? Delta R is S. Delta R is this equal to R2 minus R1. And this very small. So you can apply this formula. So if you divide this into many small delta R, Then for the whole period of the work done, F from position 1 to position 2, we sum over all this work, and sum over all this is the integral from position 1 to position 2 of F. And delta R is denoted as the dr, the diffraction derivative, okay, F dr, because it's very, very small, dr, okay, F dr. And take the integral of R from 1 to 2, and then you take this integral. It gives you the work done by the force. And this is a line integral. And if you have a plot, F depending on R, so F is not constant. If F is constant with R, you have this line, right? F constant, but F is not constant. You have something like this. F depending on R, and from this position A to position B, the work done by the force is the area of the path limit by this line and the horizontal axis. So the work done by the force is the area of this path. Okay? And in one-dimensional case, not vector, only OX. For example, you consider as the spring on this is moving along OX, you will have F equal to F depend on X dx. Okay? From this, you have this formula. From the point A to the point B, XA, XB, and then the work done, all the work done when is moving from A to B will be equal to integral is XA, XB, F, X, dx. Okay? That is the definition for the work done by the force depending on the position of the objects. So now we take another point of view. So you have this formula, okay? So now you know F from second law of Newton, you have force equal to ma. And a is the first derivative of the velocity with times, and the second derivative of the displacement with times. So to be simple, you consider the case of one-dimensional motion. OX, okay? F equal to this. Now you plug to this formula. You have work equal to integral of m d square x by dt square. That is F, okay? And dx, okay? So this guy is F dx. Use this formula, F dx, okay? So now, I use dx equal to dx by dt multiplied by dt. Is it okay? I plug to here. Then I will have is equal to m d square x by dt square dx by dt dt. Okay, and all this will be equal to d by dt of m over 2 of dx by dt square. Okay, so d by dt of, you know the integral, right? Dx by dt square will be equal to 2 times m over 2 dx by dt and d by dt of dx by dt. Okay, so do you know what is dx, d square x by dt square equal to what? D square, I think you have the cost on the calculus, so I hope you know all this already. D square x by dt square, that is, what is it? This d by dt of dx by dt. The first derivative of dx by dt, or the second derivative of x with respect to time. Okay, so this equal to m dx by dt d square x by dt square. So here you take m, this guy, equal to d by dt of this. Is it okay? And dt. D x by dt is what? Is a velocity. Is equal to dx by dt. Velocity is dx by dt. Okay? So here is integral of d by dt of, inside here is mv square over 2. Okay? You have dt here, you have dt here in the integral. So you denote as mv square over 2 is k. So actually this one is integral of dk from a to b. So this will be equal to k at b minus k at a. So finally you have work done by this force equal to delta k. So you get back the kinetic work kinetic energy theory. Changing in the kinetic energy equal to the work done by the force. Still true in the case of the force depending on the position of the object. In case the object is acted by many force, you take the sum over all the work. Okay, it's still true in this case. All right. And how about the potential energy? So the potential energy you will in different case is a gravitational potential energy. There someone is unmute who. Oh. Gravitational potential energy is, if you choose the origin is here, potential is mg and it is the height of the object comparing to the origin. Okay, and the work done by the gravitational force. Oh, sorry. The work done by the force I denote out the work by the gravitational force. All right. Equal to what? From position 1 to position 2, it will equal to mg81 minus 82. Okay. So actually, is equal to minus mg82 minus mg81 from position 1 to 2. You have to take the final one minus the first one. Okay. So here is u at the position 2 and u at the position 1. So this equal to minus u2 minus u1. So actually this delta u. So we have the work done by the gravitational force equal to minus different in the potential energy. So what does it mean? When the gravitational force did the work, it make the potential decrease. Okay. So from position 1, position 2, the potential energy is decreased. And this perform a work. So the work performed by the gravitational force making its potential energy of the object decrease, and kinetic energy increase. Okay. Vice versa. If you move projecting up this initial place and this the final place, if you moving this direction, as you moving this direction, you making the potential energy increase, right? But how about the work done by gravitational force? Gravitational force still down. So in this case, I take another color to be not confused. In this case, the work done by here is S is this direction, P is this direction. They are opposite direction. So it's minus P S. It's a negative. So when the work is negative, it makes the potential increase. So you see the direction of the sign of the work and the sign of the changing in the potential, they are all the way opposite. They are minus sign. That's that meaning. So the gravitational force making the potential of energy decreasing. Or if it's increasing, if it's negative direction to the motion is the opposite direction to the gravitational force. Okay. And also, only different in the gravitational boundary is at the initial and final that matter. So it doesn't matter you any direction. For example, in this case, you have the incline. You are starting from here is initial place to the final place is number 2 here, 81, 82, 820. So when you move to this direction, so the changing U is minus mg81. If you go this direction, or if you are falling this direction, you still get minus mg81. So when you move from the position 1 to position 2, the changing in the potential energy is the same. It doesn't matter which way you go. Which way you go. You go this way, or you go this way, or even you go this way. You will go this way, it will this way, doesn't matter. The changing in the potential energy only depend on the position of the initial place and the final place. It doesn't depend on the shape of the way you are moving. That is what properties of the gravitational potential. Okay. All right. So we can prove this. So you can read this yourselves at home. I don't want to. I don't have time to explain more this. All right. All right. So this part you read at home, and then now I summarize. I summarize you this part of this slide. I summarize what you have to read. What you need to remember is the work kinetic energy theorem. That is the changing in the kinetic energy of the object will be equal to the work done by all the force, or this work done by all the force acting on the object. So you remember only this. Okay? This first point. And the second point, you should know that the work done by the conservative force. Conservative force in this case is simple. You have the gravitation is a gravitational force or elastic. Okay. F obeying the Hooke law. You call is the conservative force. I denote at the Fg. The work done by the conservative force will be equal to minus changing in the potential. So gravitational potential, or you have the elastic potential, is a minus sign. Okay. All right. So you remember only this. So from here, for example, I can do for you some consequence. From 1, if you get the F total will be the sum of the conservative force plus F some external force, some applied force, for example. Applied force can be the up you push, or the F, make some example, and then you plug to this formula. So what do you have? Delta K equal to the work done by the Fg, okay, plus work done by the F applied force. And then you know that the work done by the conservative force will be equal minus U plus work done by the F applied force. So from this equation, you get delta K plus delta U equal to work done by applied force. So delta K plus delta U is delta E. changing in the mechanical energy will be equal to work done by the applied force. Okay? So from this work kinetic energy theorem, you can get the energy changing in the mechanical energy. So in case you don't have any applied force, some external force acting on the object. If the applied force is 0, so then you have energy conservation. Okay? You don't have any external force acting on the object. So the mechanical energy of the system is conserved. So you have energy conservation. All right? So you can derive it by yourself. The second case, in case of resistance. So for example, you have the frictional force. What happened? Frictional force, then you have similarly as this. So in this case, you have F total will be to Fg plus the friction. Okay? So you plug to 1. Then you have delta K, sorry, delta K equal to work done by G plus work done by the frictional force. The work done by the G will be equal to minus delta U plus work friction. So we have delta E equal to the work done by the friction. And you remember that the work done by the friction is by this formula. And then the friction all the way opposite direction to the direction of transition of the objects, S. So this work is a negative. The work negative means delta E is a negative. Delta E negative means the mechanical energy is decreased. Mechanical energy decrease. And in this case, the applied force normally is a positive because you apply some force. So the applied force is always have this direction. Angle is more than pi/2. So with the applied force, the mechanical energy increase. Okay? So in this chapter, you only learn work kinetic energy theory. Apply this all the times. You can get anything. So you don't need to remember the mechanical energy conservation, but you just remember this enough for you to do all the exercise concerning to apply the energy conservation. Any question? Sorry, I take some jars to my computer. Okay. So if you don't have any questions, we sorry. So you all right. So we don't have much time in this lecture to do some example exercise, but I already sent you the list of exercise. You will do apply this theory. Just should be okay. Okay. Also, Okay, so if don't have any question, we stop the lecture now. And this is also my last lectures. So I want to say thanks to all of you to attend my course. I'm very happy with your action. And I hope you will enjoy the course and don't be defer too much. And see you on Saturday for the midterm test. And I hope you can make a good revisions to prepare for the exam and also for the final one. Okay. So we stop. Yeah.
Okay. Teacher,
Yeah.
so we will not have the collision on our midterm, right?
Yeah.
Okay,
Okay.
thank you.
Just
I
to
will-
chapter
yeah.
2.
Chapter 2, I need like the collision part. All right. To the midterm test.
It's not on Saturday, right? The midterm.
Yeah, on Saturday and Miss Tu we send you the list. And then
Okay.
you base on the student number. Remember,
Oh,
student number, not the student ID. And you know the reason, right?
Okay.
Student number. Student number is on the, so sorry to I explain. So on the list, you will have the, or maybe I show you the list. Sorry. Stop share this. Wait me a second, I can share you the list and I explain you these details. All right. Okay. Stress spring. Here. Can you see the list?
Yeah.
Yes.
Yes.
Yeah, so okay, very good. So basing on the student ID here, this column. Okay. You have number 1, 2, 3, 4, 5, 6, 7 here. All right. Is it
Teacher,
clear?
can you send us this list?
Miss Tu, we send you the list.
Thank you.
I received from Miss Tu. Is it clear for everyone? All right. If something is not clear, write me email. But I hope everything already clear. I hope. And don't remember, log in at your time slot and log out after your exams. So because we don't have, we have the limitation on the login number of people logged into the Moodle. So we cannot log in at the same times more than 250 students. Okay. All right. Thank you very much for your attendance and see you on Saturday.
Bye, Professor.
Bye, Professor.
Bye-bye.
Saturday. Bye.
Bye,
Bye, Professor.
See you.
Bye, Professor.
Bye-bye.
See you next time,
Goodbye, Professor.
Yeah, see you.
Bye-bye.